Welcome to the lectures on problem solving and programming in C. This is lecture 16 and the title of the lecture is checking for special numbers. In this lecture, we will there are some we'll see we will develop algorithms to check whether a number is a particular special number or not. What are those special numbers? We'll discuss. Like in the last class, we have seen prime number, perfect number, right? There's kind of special numbers like this. We will see some more problems where we find whether a number is particular satisfy some condition or not. Okay? So in this lecture, we will see what are the amicable numbers. Okay, when do you call two numbers are amicable? Co-primes, when you call that the numbers are two numbers are co-primes to each other. What is Armstrong number? What is circular prime? So we'll try to develop algorithms for these four problems. Let us start with the first problem: amicable numbers. Amicable numbers. Amicable numbers. Numbers. Two numbers. Two integer numbers. Integer numbers. N1 greater than 0 and excuse me, n2 greater than 0 are called amicable numbers. Numbers if the sum of the factors of n1 is equal to n2 and vice versa. Vice versa. What does it mean? Let's take some example. Just taking 220 and 284. Okay, numbers 220 and 284 are examples of amicable numbers. Let's see why. What are the factors of 220? 1, 1, 2, 4, 5, 10, 11, 11, 20, 22, 22, 44, 55, 55, and 110. These are the factors. If you sum them up, what you will get is if you sum them, you will get 284. Okay. What are the prime factors of 284? Factors of 284 are 1, 2, 4, 4, 71, and 142. If you sum them up, what you will get is you will get 220. Okay. So that's what two numbers are amicable. Two integer numbers n1 and n2 are called amicable numbers. If the sum of the factors of n1 is equal to n2 and the sum of the factors of n2 is equal to n, then only we will call the numbers are amicable. So in the prime factors case, we have computed the sum of the factors, right, excluding the number in this case, but the number is also included. Number is not included. Very similar to that. Except the number, we need to compute the factors. We perfect number, in the case of perfect number, we have seen how to compute the sum of the factors of a number, excluding that particular number. So you sum them up for n1 as well as n2, and then compare n1 with n2 and n2 with n1. Sum with alternatively, and then if both are equal, then we will say the number is amicable, otherwise not. Okay, let us develop an algorithm for this. Algorithm. Amicable numbers. Amicable numbers, input two integers n1 greater than 0 and n2 greater than 0. Output check whether n1 and n2 are amicable or not. Okay, begin. So first we need to take input n1 and input n2 and n2, right? Then there is an input validation. If n1 less than or equal to 0 or n2 less than or equal to 0, then output if any one of them is less than 0, input we say invalid input. Valid input. And then stop the program. Then end if. This concludes the if statement. Otherwise, what we need to do, we need to compute the sum of the factors of n1 as well as some of the factors of n2. So let us do the sum 1 equal to 0, 0 for I equal to 1 to n minus 1 do. This logic is very similar to the way we have computed some of the factors of a number for the perfect number case. If n1, this should be n1, if n1 mod I is equal to 0, then sum equal to sum 1 equal to sum 1 plus I. End if. And then end for. Okay. Similarly, the same thing we need to do for this also, second number also. So second number also we should do the same thing. Only difference is it should be n1. Okay. I equal to, this should be n2. This should be n2. Then n2 mod I equal to 0, sum 2, this should be sum. Okay. Sum 2 equal to 0 for I equal to 1 to n2 minus 1 do. So let me redo this, write this. This should be n2 minus 1. Should be n2 minus 1. Okay. N2 mod I equal to 0, then it means I is a factor to n2, sum 2 equals sum 2 plus I. Okay. Then, then we need to compare. If sum 1 is equal to n2 and sum 2 is equal to n1, then what does it mean? Sum of the factors of the first number 1, n1 is equal to n2. Sum of the factors of number 2, n2 is equal to n1. So then it is basically output amicable numbers. Numbers are amicable. Okay. Else output numbers are not amicable. And if, then and. Right. Yes, this is the algorithm. let us continue the discussion. Let's see what is our next problem. So coprimes. Okay, next problem is coprimes. 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 Two numbers n1 and greater than 0 and n2 greater than, let's say greater than 1, not 0, greater than 1. Greater than 1 are called coprimes if they does not have any common factor other than 1. Let's take an example. Let us take 9 and 9 and let's say 4. 9 and 4. Actually, these 9 is also not prime, 4 is also not prime, but they are coprimes. So how? What are the factors? Is there any number which divides both the number? Definitely 1 divides. 2 divides this number but does not divide 9. 3 divides 9 but it doesn't divide 4. And 4 divides this number but doesn't divide 9. So the only factor is 1. Okay. That is why these numbers are called coprimes. You take some other number, 9 and 15. 9 and 15. Okay. So 9, what are the factors? 1 and 3. 1 and 3 are the common factors to this. Now, since there is an extra factor 3, so these are not coprimes. Not coprimes. Okay. Like that. So what we need to do from number 2 onwards, we need to check whether if there is any factor to this number. Okay. For example, you take 4 and 8. These are also not coprimes. It's because there is a 4 factor 4 is common. Similarly, if you take 7 and 14, these are also not coprimes because there is a factor 7 between them. Okay. That is what we need to do is from the number 2 onwards, we keep checking whether any number divides both the numbers. Then they are not coprimes. If there is no such factor, then we can say the numbers are coprimes. It's very similar to prime number algorithm. Coprimes, input n greater than 1. Sorry, n1 and n2 na. Two numbers n1 greater than 1 and n2 greater than 1. So these are basically two integer numbers. What is the output? Output, check whether the n1 and n2 are coprimes or not. Begin. Yeah, so we need to do input n1 and input n2, so that thing we can take from the previous example. Input n1 and n2. So only difference is this should be less than or equal to 1. Less than or equal to 1. Less than or equal to. Okay. So input n1, input n2, and then if n1 less than or equal to 1 or n2 less than or equal to 1, then it is invalid input and stop the program. Otherwise, we are going to see, we need to run from I equal to 2 to one of the numbers, n1. It can be any number. And then see if there is a number which perfectly divides both n1 and n2. For I equal to 2 to n1 do. Okay. Any number is fine because it may be smaller or bigger, doesn't matter. Any number, up to any number you do. If n1 mod I equal to 0 and n2 mod I equal to 0, then this one and this, both the conditions met, it means that there is a common factor. I divides both n1 and n2. Then in that case, we can say output not co-primes, not co-primes. Okay, and stop the program. And if and for. Okay, and we see, suppose if you have checked all these for all I values and none of for none of the I values, you reach this place. Obviously, your control comes here. If you are coming here, it means that none of the I values divided both n1 and n2. So it means that they are co-primes. Output co-primes. Okay, right. Then there is a end here. End of the algorithm. So read the n1 and n2, and then we checked from I equal 2 to n1 whether there is a common factor. To if I is a common factor to both n1 and n2, if the condition is true, then we say that we conclude that number is not a prime and stop the program. Otherwise, if after completion of the for loop, it means that it comes here. It means that none of the I values divided perfectly n1 and n2. So in that case, they are co-primes. Okay. Let us move to the next problem. Yes. Armstrong numbers. Next problem is Armstrong number. What is Armstrong number? Armstrong number. Okay. Let us take an example 153. How many digits are there? Number of digits. Number of digits are 3. So for each digit in the number, what are the digits in the number? 1, 5, 3. You raise each of the digits to power of this number of digits. So 1 cube plus 5 cube plus 3 cube. How much is this? 1 plus 125 plus 27, which is equal to 153, same number. So that is why the sum of the digits raised to the power of the number of digits is equal to the number. Then we say the number is Armstrong number. Let us take 24, another case. Okay, this is another case. This is first example. This is the second example. 24, number of digits are 2, 2, 2 and 4, right? And then 2 to the 2 plus 4, 4 power 2. How much is this? This is 4 plus 16. This is 20. 20 which is not equal to 24, right? So this is 153. This is amicable. Sorry, this is not amicable. This is Armstrong. Armstrong. And 24 is not an Armstrong. Not Armstrong. So what we will do is we will compute. We will compute. First thing is we need to compute number of digits. Okay, we know how to compute number of digits. We had seen that in the previous lectures. And then we need to extract one digit by one digit, either from the left side or from the right side. Anything is fine. And then take each digit and compute the power of that digit to the number of digits. If the number of digits is 3, for each digit you have to compute the cube of that digit. If the number of digits are 4, you have to compute digit to the 4. If the number of digits are 5, you have to compute digit to the 5. Okay. Then keep summing them up. Let us try to develop the algorithm for this. Algorithm, Armstrong. So input an integer number, then greater than 0, output, check whether n is Armstrong or not. Begin, input n, and then there is a input validation. Input validation will take from here. Input validation. If n less than or equal to 0, then it is invalid input and stop the program. Okay. So first thing is we need to count the number of digits. Count the number of digits. So for that, see, we in the number of digits we are going to modify the n value, right? But we need to preserve the value of n for the previous cases, previous coming. I mean, for the further logic. So that is why I take a copy of n1 in the name of n1. So digits is equal to 0 while n greater than 0 do. Sorry, n1 greater than 0. n1 greater than 0 do. n1 equal to n1 by 10. Digits plus and while and while. This computes the number of digits. This logic will compute the number of digits. Okay. Then what you need to do? We need to extract the each digit and compute the digit to the power these digits. So let us, I think we will use the count. No, we have count. I think count is better. Earlier we have used count, so we will use count here. Count plus. Okay, right. So what we need to do? While, so we need to remember some place, no, sum equal to 0. So while n greater than 0 do. What we need to do? Digit is equal to n mod 10. We are extracting the digit from the right to left because that is the easy to compute rather than extracting the digit from left to right. So we just need the digits. Order doesn't matter. So we are going with a easier method. Okay, sum equal to sum plus power of. There is a function called power. Okay, power of d comma count. Okay, this function computes the d to the count. This is equivalent to d to the count. This is equivalent to d to the count. If you do not wish to do this, we can even compute the power also. So let us, let us write that. So this is the function this is the existing function to compute the power. So if you do not wish to use this, what we will do is we will replace the statement with a separate logic. We will compute the power manually by our own logic. Okay, right. So what we need to do? Power power equal to 1 for I equal to 1 to count do d equal to power equal to power star d and for okay, it computes if I equal to 2 power equal to I equal to 1 power equal to power star means it will be power will be d. If I for I equal to 2 power equal to power star d means d square d cube d3 d4 like that, depending on the count it will compute the power. Okay, then sum equal to sum plus power. Okay, and then we need to do for n equal to n by 10, right? N by 10. Then end while. Okay. One more mistake we did is we have used n again, but we are not preserved this n. Again, n1 equal to n because we need n1 for final answer, right? So this is n1. This is n1. Okay. n1, n1. Okay. Now, if sum equal to n1 n, then output number is Armstrong. Armstrong. Else output number is not Armstrong. Okay, and if and symbol, right? So we have computed, we have read the input, and then we have input validated, and then we count the number of digits, and then we count the extract each digit, and then compute the power digit to the power of count. Digit to the power of count. This is the logic. This logic is to compute t to the count, d power count. Okay, and then you have added the sum to power to the sum, and then n is modified by n by 10 because we need to extract, we need to discard one digit. Then if sum equal to n, then it is Armstrong, otherwise not. Let us move on to the next problem. The circular prime. Last problem is circular prime. What is a circular prime? Circular prime. Circular prime. A number is called circular prime a number is called circular prime if the number if the number and all its circular rotations are prime. So what does it mean? Let us see. So 29, let's take an example. Control Z. So let us take a number 29. This is actually prime. Okay, first condition is the number should be prime. Okay, next. What is the circular rotation? 29, we can rotate like this. You bring the last digit to first. 9, 2. 9, 2. This is a one circular rotation. It's not a prime. 92 is not a prime because it is an even number. So it implies 29 is not a circular prime. Okay. So let us take some more example. 1, 2, 7. 1, 2, 7. So what are the first numbers? 1, 2, 7 is one first number, and then so you should do like this. Okay. 7, 1, 2 is another number. Then if you do like this, 2, 7, 1 is the third number. The number of circular rotations you will get is equal to the number of digits. So this is not a prime, because this is an even number. So therefore implies 1, 2, 7 is not a prime. So let us take an example circular prime number. Circular prime. Let us say all single digit prime numbers are circular primes. Let us take some number 3779. Okay. Let us take 3779. 3779. A circular prime. Prime. Because 3779, 9377, 7937, 779393. All these four numbers are primes. You can check with a tool. These are prime numbers. Primes. Okay. So that is why 3779 is prime. So so what we need to do, we need to, in this problem, we need to check whether we should have a logic to check whether a number is prime or not, and also we should be able to form this number, this circular rotation. From this number to how do you form this number? Okay, circular rotation, right? How do you form this number? So let us say, so 1, 2, 3, 4, 5. We have this number. The circular rotation will be 5, 1, 2, 3, 4. Okay. So first thing is we need to extract this portion and this portion. How do you extract this portion? This rightmost digit, number mod 10 will give you this digit. Now how do you get this portion? It will get by integer division by 10, n by 10. Okay. So this number, then what you need to do? This should be 5 to the how many digit? 1, 2, 3, 4. 5 to the 10, 10 to the 5. 5 into 10 to the 4. 10 to the 4. Plus 1, 2, 3, 4. Right? It means that the digit d into 10 to the number of digits minus 1, number of digits minus 1 plus n by 10. This is how you do to get the circular rotated number. Right? So first thing is we need to compute number of digits. At the same time, we need to compute 10 to the d minus 1. Okay, like we did for, to compute to extract the numbers from left to right. We have computed 10 to the d minus 1, right? So like that, we need to do it. So let us, there are a lot of sub-problems in this. One is we need to extract the number of digits, and we need to compute the 10 to the d minus 1. And then we need to formulate the circular rotation, and we should have logic to check whether the number is prime or not. All four things are there, right? So I will go slowly. Algorithm, circular prime, input, an integer number, n greater than 1, output, check whether n is circular prime or not. Begin. So input n, input validation is there, no? Let us take from here. Input n, and then I think this should be less than or equal to 1. If n less than or equal to 1, then it is invalid input and stop. Okay. Yes. Now let us compute the number of digits. N1 equal to n, because we need a copy of n. Otherwise, we should not modify the original value because we need the original number for the further processing. So compute digits, d is equal to 0. Number of digits, nd, okay, is equal to 0. While also we should have power, power equal to 1. I am computing number of digits as well as the 10 to the d minus 1. Okay. While n1 greater than 0 do. Okay. nd plus number of digit plus power equal to power star 10 and n1 equal to n1 by 10. So end while. So this logic is to compute number of digits. The variable is nd, it is stored in nd, and then 10 to the d minus d, 10 to the d, into the nd. Okay. But what we need 10 to the d minus 1, right? So that is why we should have power equal to power by 10, right? So up to here we got number of digits as well as 10 to the d minus. Okay. Now how many times, how many, a number will have how many circular rotations, including the original number? The circular rotations is equivalent to the number of digits. So for any such circular rotation, we need to check the prime number. So that is why we have for I equal to 1 to nd number of digits do. Okay. So now first thing is, first we need to check whether the n is circular prime or not, right? Prime or not. For I equal to 2 to n minus 1. So n by 2, we can say n by 2 do. If n mod I is equal to 0, then what does it mean? It has a factor. It means that n is not a prime number. Since n is not a prime number, n cannot be circular prime. Output not circular. Okay. Stop. End if, and then end for. right? So what if you are coming here, it means that then n is prime number. So, but we need to go for the next n. Okay, we need to form the n. N will be, we need to modify the n such that you will get, you will go for the next circular rotation. N equal to n mod 10. This gives me uh, the last digit. Okay, multiplied by power. This gives me last digit into 10 to the d minus 1 plus n by 10 quotient. This will form the circular rotated number. We are modifying the n so that for the next iteration, the n will be the circularly rotated number. Okay, n for how many, since there are nd number of circular rotation, and for each circular rotation, we are going to check whether the number is prime or not. So after this end for loop, if I not reach this place, it means that every circular rotated number is a prime number. So that case, output number is prime, circular prime. Okay, and right. So this logic is to compute the digits and 10 to the d. This is 10 to the d minus 1. This for loop is to this for loop is because we need to check how many circular rotations are there for the number. Nd number of circular rotations are. That is why we are running for nd times. And then this logic is to check whether the current number is prime or not. And this logic is to generate the next circular rotated number. So like this, we will repeat nd times. If any times we reach here, it means that the particular number is not prime, and hence the original number is not circular prime. If none of the time, if we have not reached this position for all iterations of I value, it means that every number is a prime number. So we will say, conclude that number is a circular. Okay. Let us try to translate this to a C program. A circular prime. Insert hash include cdio.h int main default return 0. This is my empty program, and then input n is there. Int n printf enter a positive integer number greater than 1. Scanf %d %n. This is the statement equivalent to input n. Then we have a if statement. If n less than or equal to 1, n less than or equal to 1. Here in mathematics, we can have, I can write like this. But in the less than or equal to symbol in C is, there should not be space. Less than followed by equal to. There should not be space between less than and equal to. So printf output statement is there. Printf invalid input, and then stop. Stop means return 0. Okay. Next is n1 equal to nd equal to 0. n1 equal to n. n1 int n1 equal to n. Int nd equal to 0. Okay, because n1 and nd for coming for the first time, we need to declare them. Similarly, int power equal to 1. There should be a semicolon at the end of every statement in C. Next, there is a while statement. While n1 greater than 0. nd plus plus power star equal to 10. This is called shorthand assignment operator. This is equivalent to power equal to power start n. This is a shorthand. This is called shorthand assignment operator. These two are equivalent. Power equal to power start n can be written like this. This is a shorthand assignment operator. N1 equal to N1 by 10. So this can also be written like the N1 by 10 by equal to 10. Okay, right. I'm using this to show you new operator. Okay, in C. There is a shorthand assignment operator that can be used like this. This saves some code. Suppose if you are feeling it confusing, you use this only. Okay. N1 equal to N1 using 10. Right. So here and then power equal to power by 10. Right. Up to here we got the number of digits and the 10 to the d minus 1. Then there is a for loop. For int insert int I equal to 1, I less than or equal to nd, I plus plus. Okay. And there is a another for inside another for. See, the problem here is one mistake is we are using I here and here also. So that is confusing, right? That will not, that create a logical error. So let us modify it to J. Okay. J should be J here. J equal to 2 to J n mod J, right? So for int J equal to 2, J less than n, J plus plus. So J equal to n by 2, na? Less than equal to n by 2. You can say less than equal to n by 2. By 2. J plus plus. Then there is if condition. If n modulus is percent, J is equal to 0. It means that n J is a factor to n. So it should be, I think, yeah, right. Yeah. Then in that case, output printf number is not a circular prime. Okay. And then stop means return 0. Otherwise, after this statement for loop, after the for loop, there is a something n equal to n mod 10. N mod 10 is percent 10. 10 multiplied by power plus n by 10. Right. So everything is done. Outside this for loop, there is a printf state. Printf number is circular prime. Okay. Let us run this program, compile this program, GCC circular prime dot slash dot out. Let's give 7. 7 is a prime number. If you give any prime number, it will say circular prime. If you give non-prime number, it say not a circular. Let us give some other prime number, circular prime number. The circular prime is let's say 3779. 3779. It's a circular. So let us say 29 is not a circular, like this. Okay. So this is input is read, input validated. We have computed the number of digits on the 10 to the power d minus 1. And then since we have nd number of circular rotations, and for each circular rotation, we are checking if the number is prime or not. If it is prime, we are displaying that number is not circular prime and stopping the program. Otherwise, we are preparing the next circular rotated number. With this statement on 37, we are preparing the number which is equivalent to the next circular rotation of the previous n. Like this will be done nd number of digit times, so that all circular rotation numbers are checked for their prime number test checking status. Okay. I'll stop here. Thank you.